Howdy. I'll start by saying that there has already been quite a few conversations about rollups and how they are relevant to IBC. So I'm going to try to be a little bit unique here, and instead of pitching my solution, I'm going to go from an engineering perspective and offer why I think this is a very interesting problem, why I think it's more challenging than people give it credit for, and actually why I'm a little bit concerned that we're going to start neglecting security in replacement for good UX, which has actually been a common thread for rollups for a long time, with this promise that we're eventually going to have these perfect proofs, and they're not really coming. And so I would like to sort of address what the current sort of format looks like, especially with Celestia, what we're thinking about, and then sort of talk about what are the sort of challenges we're facing at the moment and how we're sort of trying to solve them. So to start off with, I will give a brief overview of these systems. So it's going to be very common knowledge for all of you, I hope, but both of them are sort of derived by this blockchain concept. So you have a linked list of transactions, and then you have this like deterministic state machine that runs through every single transaction, and in between it produces a state. And now the state thing is the important thing that we want to know about the world, and we want to make sure that it is verifiable so that we can all sort of trust it, verify it itself instead of trusting it. And so this sort of blockchain thing is split into two different components. You have the serializing thing and executing. And so in a consensus or a committee-based system, those two things are both done by consensus. So your validator set agrees on two things at the same time. It is agreeing on the set of transactions that go into a block, and it is agreeing on the state of the world. And now how that differs with a rollup is that the serialization aspect is outsourced to a consensus system, which is known as a DA layer, and then the execution is solved through proofs. And I think it's very important just to understand why we still need this like consensus layer here. So if you imagine a standard sequencer, a centralized sequencer, what's to stop them from equivocating? So you have this classic problem in a lot of computers, sort of computer science called split brain, especially in the distributed systems where you have someone producing two different versions at the same height. And in this case here, imagine someone is producing blocks, and they produce a set of blocks, and then they give one to the light node, and then the other set of blocks they give to the honest full nodes. And so now this light node, who maybe was relying on an optimistic fraud proof, is waiting for that to happen, but no one else has seen it. So no one else can provide that fraud proof. That light node then assumes that it's valid, even though it's not, and then is fooled. So we need to have some sort of consensus that agrees on the canonical ordering of this. I want to also just briefly touch on proofs. I'm not going to go into the details of them, but I just want to know from the black box sort of model here, we have kind of two types of proofs that are very popular at the moment, or like the main sort of one. So one is a fraud proof, and a fraud proof just proves that something is false. So you can't actually prove something is true. You just prove that like bad state or like app hashes are fraudulent. And so that the way they work is that we optimistically trust that everything's going to be good, and then someone will then submit a fraud proof so that there is at least one honest full node. On the other hand, we have validity proofs, which can only prove that something is true. And these are a lot more powerful because of that, because someone can submit a state and then automatically prove that that is true without having to wait. And so trying to summarize all this here and maybe sort of bring the case about why these proof-based systems are actually needed in the first place and actually help with both security and scalability. Our sort of classic consensus engines, our BFT consensus, has a fault tolerance of n divided by 3. So 1/3 of the system, if there's more than 1/3 of the system failing, then you lose the sort of securities of having a canonical chain. And so in order to prevent this, we usually have large systems of like hundreds, maybe possibly thousands of nodes operating. If you were to compare that with non-BFT systems, or Raft that like other sort of more corporate systems use, those only have maybe 10, 15, because only half of those need to be faulty, and we don't really care about this like Byzantine aspect. So in comparison with consensus, fraud proofs is n-1. What I mean by that is as long as there's one honest full node there that can provide the fraud proofs for it, you have the security that you will not like trust a state that is incorrect. And so we can also reduce the size of the amount of processes running for this. And then in the sort of ZK world that we're hopefully heading towards, we'll have a validity proof in which I sort of say that with an apostrophe here, but like you can have the entire system be faulty. There can be no honest nodes, and you won't trust it until an honest node produces some sort of proof of it. So you're just going to wait out till that happens. I guess like the apostrophe is in terms of liveness. But in terms of security, you're not going to trust something that isn't valid, and that is very important. So we can also reduce the size even more. And reducing their size is a sort of another way of saying that we can sort of scale the system. We can process more transactions, and this is kind of what the appeal is with rollups. But now we've sort of talked about that, let's sort of turn to the interoperability aspect. So how do we solve this where we have this current ecosystem of a lot of consensus-based nodes? How are they now going to sort of talk with this growing ecosystem of rollups? And so at least my take on this as well is that the goal of interoperability is to have a verifiable means of knowing the state of another chain. Like, that is the single most important thing. Once you've got that, I think everything else is kind of like trivial in terms of like knowing that, okay, this is the state of that chain so that I know that executed, so I can do my acknowledgements, and I can do my timeouts, and so forth. And so the naive way of doing this is to just run a node on every other chain that you're connected with. And some solutions do this already. You have the likes of like Axler, that if you want to have some sort of generic way of proving every other state machine is that you basically have to run a full node on every single other system. And so that definitely doesn't scale. There are worryingly even worse in which people are just trusting that the counterparty state is correct, which is very concerning. And so what we need to have is some sort of way with which we can scalely sort of prove the state of the other chain. And so just sort of going back to like why this is important and just covering the basics of IBC, I guess, is once we work out the app hash of another chain, and we know that's commitment structure, it can sort of vary depending on the blockchain itself. We can work out, for example, the state of a certain module. So this would be an IBC module like the transfer. So we can work out what is in the queue, what packets are waiting to be sent and have been received, and what is sort of like an escrow. So once we can prove the state of another chain and we know that they have received this, then we can actually perform our state execution functions on the local chain. So it's very important to know this thing. And the way that we do this, as Aditya sort of covered, is through this like client abstraction in IBC. So a client, and I'm going to use sort of the consensus to consensus start with, is that we have client B, which would be like a tenement-like client on top of chain A, and then alternatively, client A on top of chain B. And so client A is used to verify the state of chain A so that chain B can then process those state executions, and then client B does the reverse. So this is the vanilla case. We all know about this. Okay, so what happens if it's a rollup? Well, you still have one-way bridging because rollup B can have client A's state. It can still use the tenement-like client. It can still verify those signatures and realize what chain A state is. The problem is you don't have it the other way around. So I guess the obvious answer that I'm pointing to here is that chain A needs to have a rollup-like client. And now that's very easy to say. There's actually a lot of complexity in trying to achieve this. And so once we have this like client, we can sort of verify the app hash of that rollup or whatever sort of like state that's represented. We can prove the transfer module or whatever sort of IBC module we're wanting to engage with, and we can start sending messages across. Okay. So to break up what that like client, rollup like client looks like, I'll go through sort of the order of events of a sort of typical token transfer. So we have a submission of the transfer on rollup A, and the funds get escrowed. Then a packet arrives on chain B to mint the tokens. So one is getting locked, and another is minting new ones. So then an app hash arrives on chain B, proving rollup A has correctly escrowed the funds. And then we then have these two parts here, D and E, which are very important, which is that we prove through inclusion that the transaction on rollup A was published by the DA layer. So that is the first step. And then the second step is then we prove the app hash of the rollup A through a fraud of validity proof. And there's actually, we can divide these into two types of clients. Aditya's talked about the sort of conditional clients here, where first we have to sort of satisfy the DA-like client, and then we satisfy the rollup-like client. In addition to this, if we're using some sort of shared sequencer, we may also need a shared sequencer-like client. The reason being is DA may decide the inclusion of the transactions, but it does not decide the fork choice rule. And so it could be that the way that those transactions are interpreted could be different to what is just submitted on the DA chain. And so not only will you need to know that it's included, but it was actually interpreted correctly according to the fork choice rule. And then finally, if that was included, that you have this sort of proof system to say that the app hash that was follows from that state is correct. Okay. So to start off with D, and to sort of go a little bit deeper into this, everything is a Merkle tree, and so is this case for most DA layers and for Celestia. So we have this DA data root. And the way we sort of construct a block is a little bit different to help with sampling, and we sort of break it out into these chunks, evenly sized chunks, and we call it a square here. And so each square is made up of a bunch of namespaces, and each rollup posts their data to that namespace. So in order to prove that the transaction was included, we need to get a Merkle proof to one of the leaves here. So I've just said this rollup transaction. And so that, first we need to know the app hash of the DA layer. So that needs to be on chain for that consensus chain. And then with that, someone can submit a transaction saying, hey, this rollup transaction was included. And so that's the first step. And then the second step is to prove the app hash of the rollup through either a fraud or validity proof. And so here we sort of wait out until we sort of receive the app hash, and then we wait for a fraud proof for any challenges to come in. And so if there is a proof submitted, then we know that, okay, we reject that transaction. There's still a lot of thought that needs to be done into how we sort of process this now. The moment the default is just to sort of no longer trust that client, and we sort of freeze that. That works well for consensus clients, but there's actually the ability for rollups to recover. Like just because a sequencer was bad, you can still just fork off that chain much easier than you can a tenement chain. Tenement doesn't, in this protocol, really allow for forks. And then for validity proofs, there is no fraud proof window, of course. The moment a proof is submitted proving that, you can then go and execute all the callbacks on the pending packets. So if you're waiting for that transfer to be validated, now you can go do this. So the validity proofs have the advantage of being a lot faster. Of course, they're a lot more in size. Cool. So now I'm going to sort of talk. That was the high-level idea of like how that system will look like in an IBC world. Now we're looking at what are some of the challenges and sort of and emergent properties of this. I'll start with the kind of good things. So having a shared DA layer has a lot of advantages. And from the rollups perspective, what you have is if you're connected to all these consensus chains, you're going to have these headers, or I'm including both the commit and validator set here, in the rollup block or in the DA block. And so we can kind of share that data around. We don't need to post it for every single rollup. So prior, we would have every single chain post every other chain's headers. Now we can just post our own header and almost like the same way that pointers work, point to other headers. So rollup A and rollup B can also just point to chain A to get the validity of that app hash and don't need to like, submit it multiple times. There could be other rollups that aren't even involved in this block that can also use that as proof. And so what we get, and the same with the validity and fraud proofs, so not just the consensus headers, they can also post this. So I only have to post my validity proof one time. I don't have to post it on every other chain in the shared DA world. I just post it once, and then all the other rollups who are connected to me can read that, and then if they validate it correctly, can then execute it. There is also advantages from the consensus chain side. So if we have a single DA-like client, so this is this multi-client model where we're separating the execution from the inclusion. We have the same DA-like client can prove inclusion of multiple transactions from different rollups. And so you don't have to have multiple DA clients. You can just have one. And then on top of that, you'll have each of the execution clients. Now, the problem with that is the tenement-like clients are relatively small in respect to having verification systems and proofs. And so the fact that we have a single DA layer isn't much of a consolation to how large it's going to have if you have 100 connections, so 100 different rollups. And for each rollup, you need the verification system, and then you need to have some way with which these giant proofs can come in as well. And so it's going to be a lot more gas heavy. Like if already we're seeing these sort of interoperability protocols which are trying to remove out a lot of the signature verification and a lot of the verification that we rely on, and this is going to be a lot more taxing. So what we might see, and we're already seeing with the likes of Polymer as a good example, and the Dimension Hub, is to a convergence of hub and spoke model, where you have a single chain which is responsible for having all the verification systems of all the rollups, and then all the rollups first interop with the hub, and then move on to the other chains. This does, of course, bring across the extra risk now. So you're no longer, if I'm rollup A and I can care about rollup A and chain A, those are the two worlds, or the two communities that I want to be associated with. Now I've got this third-party risk. You've also got the third-party risk of that DA layer. And so now we've got this model where we had this very simple world of a proof of stake where the validators were supposed to be aligned with, based on their stake, based on how much they care for that ecosystem. And now we're going to have a whole bunch of other people who sort of verify things who aren't maybe as aligned and could have alternative interests, and we'll be unaware of when that happens. Another idea is to sort of get to a more modular or generic verification system. So if we can use the same verification system across different state machines, and we can find what are the common threads, then perhaps we can have one consensus chain be able to verify lots of different state machines on the other chains. I think another very important issue is the issue of upgrades. So conventionally, we have a committee, and the committee always signs on to what the next committee is, or the validator set signs on to what the next validator sets. And so we're always agreeing on the next state machine is by doing that. And so if we're doing an upgrade, what it simply happens in the consensus world is that they just vote on this is now the new state machine. But how does this work with the rollup? First, if you're a client and there is the state machine of the V1 rollup, and then they're trying to move to V2, that means you're going to have some way of swapping them out. Now, if you haven't got any dynamic way of doing this, that means those transactions, that connection between that rollup and that chain stops. And you have to wait until you do a system upgrade, until the network upgrades, so it has now the V2 client that you can start verifying these transactions. So the obvious sort of route that I think people are looking at now is to have something WASM-based. And so there is already evidence of an IBC WASM client. And so what we might see is each sort of consensus chain having this WASM platform with which verification systems can be uploaded on. And then those verification systems can then verify proofs that come in based on certain chains. There is another even more significant issue here, which is who decides when to upgrade and what the correct verification system is. And so, as I said, with the consensus, we sort of trust in that, and if we don't, we can just sort of stop. So we realize, okay, they've moved to V2 and we disagree with that, so we're just going to halt. The thing with the rollup is, do we trust the sequencer? If so, then the sequencer can arbitrarily change the state machine. They can go from V1 to V2 to V3, and they can introduce logic that doesn't, the rest of the community doesn't agree with. So what we might end up seeing is requiring sort of upgrades to happen on chain. So every single consensus chain will now have to agree, hey, do we want to choose this V2 state machine of the rollup, or are we happy with V1? And then are we going to do that for every single state machine if there's 100 networks? And so yeah, this gets a little bit difficult, and I think there's a lot more work that we need to do in working out, okay, how do we actually choose when to go from one state machine to another? This is something where currently IBC doesn't really support forks, and it doesn't quite have to, because Tendermint is supposed to be fork-proof to a certain extent, but that's not the case with rollups. Rollups, we can see lots of different forks, and there can be lots of interpretations. It's very subjective about which to follow. So I think this is another challenge that they're going to do. That is all. Those are, I hope that was helpful for some context from an engineering standpoint. Ask if any of you have any questions. If not, thank you very much.